so JS of A and B, where A and B are two sets, is equal to, and I'm going to write it out, the cardinality of A intersect B over the cardinality of A union B. I mean, that's hard to come up with a simpler definition than that, and one that would seem like it makes more sense. So now let's think about examples of Jacquard similarity. So if A equals B, it's 1. Okay, that's cool. If A and B are completely disjoint, it equals 0. Also, that's pretty good. Now let's think about the middle ground. If A is twice as big as B and contains all of B, then the Jacquard similarity is going to be a half, right? Because the intersection will be B, the union will be A, which is twice as big, so that will be 1 over 2, which is a half. So also, I'll just write that out. So if A is 2B and A contains B, then JSAB equals 0.5. Now also, if A equals B and A and B share 2/3 of their elements, then JSAB also equals a half. Okay, so we don't need to think that one through. A intersection B is 2/3. A union B is 4/3, right? Because each part has a third that the other part doesn't have, right? So you have the intersection, which is 2/3, plus the two parts that they don't have, which is 4/3. So 2 over 4 equals a half. Okay. Now, I don't know how intuitive that is. To be honest with you, this versus this in terms of intuition, I still don't have it. Like, I don't have why they're the same and why I would want them to be the same. But whatever. It gives me a metric. All right, that's my metric. I should look at my notes. Sorry. Oh, I have internet. That's a good start. There we go. There we go. Okay, blah, blah. Okay, now, let's suppose you want to implement Jacquard similarity, okay? You're gonna read in two sets, any way you read in two sets, okay? Let's just say they're strings. What are you gonna do? Gun to the head. What are you gonna do? How are you gonna implement it? Okay, gun to the head, and we'll wait 15 seconds. 15 seconds you're gonna think while you contemplate your life, but also think, if Dr. Planck made me implement this, I have two files that contain names. I want to calculate the Jacquard similarity of these two files, right, where each name is an element of a set. What's my data structure? Oh, I like disjoint sets. Unfortunately not. We'll talk through it. It's a good thought. Set. I'd go set. Even unordered set to start with, right? What do? You take all the elements of A, put it into a set, ordered or unordered. Every element of B, call find on A, right? That will tell you the size of the intersection, and then you can just calculate the union, right? You know how big both files are, right? So A plus B minus A intersect B equals A union B, right? Because if I take the size of each set and add them up, it double counts the intersection. So I can calculate the size of A, I can calculate the size of B, I can do A intersect B easily with a set. Okay, got it, done. What's my running time? It's n log n, right? It's our favorite, n log n. Now, if it's an unordered set, it's O of n, right? And we don't need it to be sorted, okay? Although we'll talk about that in a little bit. Okay, so running time, O of n log n, or O of n, depending on whether you're sorted or unsorted. Okay. gun were to your head again. We have a lot of guns to our head. Should we kill you or your family this time?
My family.
Your family? Okay, I see. So, here. Here, let's create two sets. Random names. What do we do? Let's make it 100. 100 into f1.text. Now what I'll do is I'm going to take, I'll say head-n 50. No, let's do 75. No, let's do 67. f1.text, put that into f2.text, and then let's say random names 33, and append that to f2.text. And here. Okay, so this one's got 100 names. Always starts with a good one, doesn't it? Let's randomize that. Boom, randomizes it. Okay. And here we also have 100 names. Let's randomize these guys. Okay. What if I wanted to use a shell script to calculate the Jacquard similarity? How would we do it? Okay. Well, I know, right? I can do the size of A, right? Here, I'll even move it. f1.text goes into a.text, and let's move f2.text, bless you, into b.text. Okay, I know how big the files are, right? wc a.text, wc b.text. How can I calculate their union? You can do it. You can do it. Unix tool.
Diff word count.
Diff word count? Oh, diff. Well, that's a good idea, Jamin. I like that idea. But it's wrong. I'm just kidding. No, it's actually a very good idea. I got one that's cleaner, though. Sort-u. Cat them together, call sort-u. Right, so if I cat a.text and b.text, pipe that to sort-u, pipe that to word count, that tells me the number of unique words. That's the intersection, or that's the union. Okay, so now from the union, I can calculate the intersection, then I can calculate the Jacquard similarity, which we know here, right? We know that the union is 67 because we created it. So if I calculate 67 over 133, it's roughly a half. Okay, so that's nice. Now, we'll talk a little bit more about making things fast. Now let's go into min hash. Okay. Now, min hash is a probabilistic algorithm, as the name hash implies, okay? And it's based on this incredibly elegant fact. Elegant and useless. We'll get to it, okay? This is the one that Emmerich said in his talk, right? That got me thinking about this in the first place. And the idea is this. We're just going to state it. If you hash every element of of A, and hash every element of B, and you look at the minimum valued hash of each of those, the probability of those equaling each other is equal to the Jacquard similarity. Elegant as shit.
Can you repeat that one more time?
I will. I could even write it down. Right? So here, I'll write it down. Okay. If you hash every element of A and every element of B, and compare the two minimum hashes, then the probability of the hashes equaling each other is the Jacquard similarity.
Why does it have to be the minimum? Could it be the max?
Could be the max.
Okay.
Could be the max. The whole minimum, all right, so here's one of the things that's crazy about this algorithm, in my opinion. What is hashing? I mean, what is hashing? When I take some element of anything and I hash it, what do I get? I get a random number, right? And the random number, the randomness is important because the randomness is how I avoid collisions. So, who the crap cares about the minimum value? It just seems taking random numbers and a minimum value. But the idea behind it is we want to choose one reliable value from each set and then compare them. Now, we can prove this. It's a super easy proof, right? Which I haven't ever done before because I never thought about it, but I was walking yesterday prepping for class, and I was like, holy shit, this is easy. And it just came from examples. So now let's go for the examples, All right? Let's say A equals B. Their minimum hashes are the same, period. Right? There's no and we're going to assume we're not going to have any hash collisions. So let's say we're just using MD5. We're never going to have a hash collision. Okay? So if they equal each other, yeah, the two hashes are going to equal. Probability 1. If they're completely disjoint, then they're going to have completely different sets of hashes, and there's no way they can equal each other. Okay? 0. Got it. Now, let's think about the example where A is twice as big as B, and A contains B. All right? So let's give an example here. Let's say A equals 1, 2, 3, 4, 5, 6. And let's make it even simpler. Let's just do 1, 2, 3, 4. Okay? And B equals 2, 3. If I take these hashes and I sort them, what am I doing? I'm just putting them in a random order, right? Whatever these hashes are, there are only going to be 4 of them, right? Because 2 and 3 are duplicated. And the order is going to be randomized. So you've got a 25% chance of 1 being the minimum, or 2 being the minimum, or 3 being the minimum, or 4. So look at it. You got a 25% chance of 1 or 4 being the minimum. That means the hashes won't match. Plus, you got a 25 chance of 2 and 3, and the hashes will match. 50%. Okay. Let's look at the other example. Let's say I've got A equals 1, 2, 3, and B equals 2, 3, 4. Okay. Right now they're the same size, and one has 2/3 of the other, so I should be 50%. It's the same thing, right? We have 4 potential hashes. The ordering is going to be random, so the probability of each one of these being the minimum is the same, 25%. So we have the exact same thing. 25% 1, mismatch. 25% 4, mismatch. 25% 2, match. 25% 3, match. 50%. Okay? So now let's just go to the definition in general, right? So how many hashes, unique hashes are there? Well, A union B. Right? It's gotta be. Each one of these has an equal probability of being the minimum hash. Okay? So what does that mean? So how many hashes belong to the intersection? Well, the number in the intersection. Right? So the probability of them matching is exactly the intersection over the union. Just what you want. And whoever came up with that was pretty smart, I think. Now what they did with it wasn't. Okay. In fact, what they did with it is they went all theory. And I like to beat on theory. I like theory, but you got to beat on theory sometimes. Okay? So, all right. So now do we understand min hash? And the bottom line of min hash. Probability of the minima matching is equal to the Jacquard similarity. Okay. So how do we make use of this fact? So here, let's make use of this fact in the most useless way possible. And this is the first thing that they teach you in Wikipedia. Okay? We've heard of the law of large numbers, yes? If we haven't, would you like me to express the law of large numbers? Yes. Dr. Planck's version. Okay, so I'm sure this is not Wikipedia's version, this is mine. But basically what the law of large numbers says that if you're collecting samples from a probability distribution, so I'm choosing random numbers according to a probability distribution, then as the number of numbers that I choose approaches infinity, that's the large part, okay, my sample mean will be the same as my probability mean. So basically, if I keep sampling enough, then I can draw conclusions from it, right? And this is how Vegas makes money, right? This is how I make money, gambling on sports, right? Because I'll only gamble on sports when they give me enough that I have a statistical edge. And if I then bank on that, I will make money over time. And I do, and that's fun, because I like making money. Not a lot, but it keeps me happy. And it keeps me superior to my son, right? Who just doesn't have the discipline not to bet according to his gut. It was great. Aside, does anyone care about college basketball here? Okay. Wake Forest was a 2-point favorite over Duke on the sports blinds. Duke was what, top 8? And Wake Forest was unranked. Okay? Yet Wake Forest was a favorite, a 2-point favorite over Duke. My son calls me. He's like, I got a lock, man, I got a lock. He's like, Wake Forest is a 2-point favorite over Duke. That's moronic. I gotta put it on Duke. I'm like, no. Whenever you see, there's a rule. Whenever you see a line that makes no sense, you bet the nonsensical part. He's like, that doesn't make any sense. I was like, how many yahoos are like you seeing that line and betting on Duke, right? So that line is already pushed way far towards Duke, and yet they still have Wake Forest being a thing. I said, I'm doing it right now. I said, I'm going to put $10 on Wake Forest, and you're going to call me later today saying, damn, you were right. He put 35 on Duke, and Wake Forest won. I mean, it doesn't always happen. It's statistical, right? Now, I don't usually do that. I'm usually much more lame with my statistical betting. But that one is also fun because I got to lord it over him. You know, and he got to lose money. Okay. So how does this affect min hash? Well, what this means with min hash is as follows. This is what's crazy. Let us say I choose k hash functions. We've heard that before, right? That came from Bloom filters last time. So if I use k hash functions, then I can sample. Right? For each hash function, find the minimum hashes in both sets and compare them. Right? Assign 1 for a match and 0 for a mismatch. As k goes to infinity, the average will equal the Jacquard similarity. Okay? Standard sampling story. Right? Now, the theoreticians, I haven't done this. The theoreticians have done this one. So, but let's think about running time overhead. Okay? Let's say computing a hash function is O of 1. Okay, of a value. And let's say, so hash computation is O of 1. We've got n items here. Let's go. A equals B equals n. Okay. What is the runtime complexity of min hash? Did I hear someone say kn? Yep. Simple, right? You just go through everything. N items, hash them. The minimum calculation is O of 1, right? You're going through it twice. 2 O of n is O of n, so we're good. Okay, K of n. What's the space complexity? What am I maintaining for A and B? When I have one hash function, okay, what am I maintaining for A when I'm calculating it?
Hashes.
How many hashes do I need to store? 1, the minimum, right? I'm going to go calculate the minimum. Just all I need is the minimum. As I calculate something smaller, now that's the minimum. Okay, so the space is O of 1. Even for the k hashes, right? Because I do it once for each hash, right? And then I throw away my minimum because I've made the calculation. Okay, now the theoreticians tell me that the error in this is roughly 1 over square root of k. All right, now let's think about this in terms of Bloom filters. Remember Bloom filters? What was my error? Like when I had 10 times the size and 7 hash functions, my error was like 0.008. Okay? Let's think about this. If I want my error to be 0.1, 10%, how big is k? 100. If I want my error to be 0.01, how big is k? 10,000. If I want my error to be 0.001, what is it? It's 1,000,000. That's pretty freaking big, right? Especially if I'm comparing it to using a set, right, or an unordered set where it's O of n. Right now I'm taking kn and k's in the millions. This is why this one's stupid. Okay? It just is. It's elegant as all crap. Okay? But it's stupid. We're going to explore that even more. And it was the hardest to implement. By far, it was the hardest thing to implement. Okay. This is called min hash with k hashes. Okay. And as always, yeah, Prana.
What exactly is the min hash? Like, what is it looking for?
So it's a bizarre thing. You take all your values and you hash them. Let's do it. Here we go. A.text. So that's right. A.text and B.text both have this. They share 2/3 of their elements. Okay. Well, so let's suppose I want to hash each one of those. So here, whoop, echo that. Into OpenSSL MD5. Okay, there are my hashes. I'll sort them. There's my min hash. Okay, that's my minimum value. We don't even know what value it corresponds to. But now let me go over to B, right? So cd temp min hash. I'm typing poorly today. Okay, so here, vib.text. Here, let's do it all in one thing. Echo 1 into OpenSSL MD5. Are we all good with this? Are we all good with this little substitution that I've done? This is like a sed command. So what this says is grab everything. Wildcard dot star, wildcard star, put it in the backslash parentheses, store it, and now substitute that with echo. Remember, pipe to OpenSSL MD5. That gets all those. Now I go ahead and pipe that to the shell. Okay, sort. There it is. They match. We got lucky because they match. If you look at the second ones, they don't match. Yeah.
Would you not be able to just sort the original set and find out if they have like the same minimum in the original set? Because when they hash to the same thing anyways, or?
Yeah, although this works with general values rather than, so now think maybe your values are pages or something that's really big that you don't want to sort. So you're absolutely right. You could sort the values. You could actually sort you could hash them and sort the hashes, right? And then look for the hashes, right? Which would be different than min hash. Okay, those are all excellent ideas. We have to evaluate all of them. But I mean, we do implement that. So, but those are good questions. And as you can see right here, right, the second hashes don't match. Right, so it's not like all the hashes are the same. Now, how would I use the different hash function? I'll get you. How do you get a different hash function? Here, let's put a lowercase a in front of every name. So, echo, substitute echo with echo a. There. Same thing here. Echo, echo a. Right? That's a different hash function. Right? It's the same thing we did before. I'm salting the value. Right? So now, if I pipe that to shell, pipe that to sort, pipe this to shell, pipe this to sort, maybe they'll equal each other, maybe they won't. Kind of hoping they don't. Hey, they don't. So we got a miss. Right? So our probability of a hit's going to be 50%, because that's the Descartes similarity. Okay, Matthew.
So if the error's so high and like a runtime bad, you fix the error, should we care at all about min hash?
No.
Okay.
Absolutely not. Sorry. That's why this lecture is useless. Crack on Emmerich on Thursday, though. He loves min hash. So you should crack on him. Tell him he doesn't know what he's talking about. He likes that. He'll tell me I don't know what I'm talking about. He's done that many times. Yeah?
Could it just be phrased as grabbing two random elements equal each other?
Yeah. Well, no, because it's not just two random elements. That's where the min part of the min hash comes from, because it really is grabbing two random elements that they have to correspond to each other. right? And this whole minimum hash thing is what makes them correspond to each other, right? And it would not even work if you said, if you said grab the third minimum, and even if the set's at the same size, if you say grab the third minimum and make that equal, I bet the theory doesn't hold. But the fact that it's the minimum means that every element has equal probability of being that minimum. You could say every element has equal probability of being third. Maybe. That might be actually why one hash function works. Sorry. Yes, Justin.
So if the values are already sorted beforehand, or if they're random beforehand and you hash them all, do you not need to sort them and you can just get the first value?
That's the thing, right? That's where you get the O of what you don't have to sort because you're just keeping track of the minimum. Okay. Now, this version sucks. We'll display that it sucks more. There's a second version that it comes afterwards in Wikipedia. Okay, and this one is called, there we go, min hash with one hash function, which makes me feel more comfortable to see there's one hash function. And what you do here is, now you hash every value, and for each set, you maintain the k smallest hashes. Okay, so we got k in there again, but now we're not having to hash a bazillion times. We just hashed once. We're going to store the k smallest value, and then the Jacquard similarity of these two sets, k hashes, smallest hashes, approximates the real Jacquard similarity with the same error. Okay, so now the difference, right? The difference is now I've got before I was only keeping one value, the minimum, and then comparing them. Now what I'm doing is I'm keeping k values, which are the k minimum, and then I'm going to calculate the Jacquard similarity using whatever, a set, something else, some other way of doing it, okay, of that. And it approximates, and I have the same error bound. So now this is a little bit more comfortable, right? If I want an error of 10%, then I've got to keep 100 hashes. If I want an error bound of 0.01, then I got to keep 10,000 hashes. But that all seems reasonable. Okay. Now, how does this work? I don't know. I can't tell you the theory. I can't prove this one. I just trust the theoreticians on it. Okay. This one also has a much nicer property. I'll write this one down. This has a really nice property that as k approaches a, the JS, right, the error goes to 0. Right? Because if I do the entire set, then I'm just calculating the Jacquard similarity, right? It's not giving me any savings, but I'm actually doing the exact calculation. Whereas this one, that's not true, right? Because this one, I'm always doing this hash and compare the mins, and so I got to just keep doing it. And so I could do it a bazillion times, and the error is probably still not going to get down to 0. So that's a nice part about this one. Okay. Jamin.
Is the space complexity for this one O of k?
Yes. Let's talk. We can talk about running time too, but let me get Matthew.
So is this version basically faster with more memory overhead?
It's faster. Yes. Yeah. There's a good trade-off, and yeah, we can talk about that, right? So what is this now? This is going to be O of n log k, right? And why is it n log k? Because how am I going to implement this? I'll use a set now. I can't use an unordered set because I really care about them being sorted. So what I'll do is I'll just keep inserting these hashes into a set, and then when my set size gets bigger than k, I delete the maximum one, right? So that I'm always maintaining a set size of k. And then when I'm done, and if I do this with both of these, okay, with both A and B, now actually I can run through both of those sets and calculate the Jacquard similarity in a linear fashion, right? Because I have two sorted sets, so I can just run through and say, all right, if this is too big than that, then I need to increment this. If this is too big, I need to increment this. If they're equal, cool, increment them both, right? So that's going to be O of k, right? So time complexity here, RT,